We'll start in about a minute. All right, we'll finish up the section 1 from chapter 11 on sequences, and then we'll start infinite series in section 2. 1 week from today, we'll have a test. Test 3, it will be over sections 10.1 through 10.4, and also 11.1 and 11.2. Okay, we left off looking at sequences, where the nth term of the sequence is defined. And we can compute the limits of these sequences. So the next one, what does the sequence converge to, or does it not converge? So if we compute the limit as n approaches infinity of 2n minus 1 over 4n to the second plus 1. So borrowing what we did in Calc 1, the term with the largest exponent in the denominator is 4n to the second. So if we multiply the rational expression by 1 in the form 1 divided by n to the second over 1 divided by n to the second, we can write this as the limit as n approaches infinity. So in the numerator, we get 2 over n minus 1 over n squared. In the denominator, we get 4 plus 1 over n squared. And then we observe what each of those 4 terms do as n approaches infinity. So both terms in the numerator go to 0 because the numerators are constants, but the denominators are approaching infinity. So the numerator goes to 0. The number 4 is unaffected by what n does, so 4 just remains 4, and then plus 1 over n to the second. 1 over n to the second goes to 0, and 0 divided by 4 is 0. So the limit of this sequence is 0. Okay, the next one, a sub n, the nth term is 3 to the 1 over n. So maybe, just in case it helps, I'll list the first few terms in this sequence. So a sub 1 is 3 to the 1 over 1, or 3. A sub 2 is 3 to the 1 over 2, or 3 to the 1/2, and so on. If you just list the sequence without using the a sub n terms, then the terms in the sequence are 3 to the 1/2, 3 to the 1/3, and so on. Those Those are the numbers in that sequence. Okay, to determine if what the limit of that sequence is, the limit as n approaches infinity of 3 to the 1 over n, we can write this as 3 to the limit as n approaches infinity of 1 over n. Something that you may have seen in Calc 1, that kind of thing. And then the limit of 1 over n as n approaches infinity is 0. Right? As n gets large, the denominator gets large, which means 1 divided by a large number gets close to 0. So this is 3 to the 0, or 1. So the limit of that sequence is 1. The next example, the nth term is n to the 1 over n. So the first few terms in this sequence, 1 to the 1 over n is just 1, 2 to the 1/2, 3 to the 1/3, 4 to the 1/4, and so on. Okay, for this one, we can borrow what we learned in Calc 1. The related function of x is x to the 1 over x, where x is a positive real number in this case. So for x greater than 0. So another way to express x to the 1 over x is I can replace x with e to the natural log of x, and we raise that to the exponent 1 over x. Okay, then applying properties of exponents, we can write this as e to the 1 over x times the natural log of x, which we can write as e to the natural log of x over x. Okay, so the related limit, we want to find the limit of this sequence where n is a positive integer. But the limit of this, as x approaches infinity, will be the same number as the limit of the sequence. So the limit as x approaches infinity of e to the natural log of x over x, this is the same as e to the limit as x approaches infinity of the natural log of x over x. Okay, so what do we do with the exponent, or that limit? The limit as x approaches infinity of the natural log of x over x. Well, we'll note that the natural log of x approaches infinity as x approaches infinity, and in the denominator, x approaches infinity as x approaches infinity. So we have one of those indeterminate forms, infinity over infinity, so we can apply Hopital's rule to that limit. So let's see. I might have enough space here. So when applying Hopital's rule, we take the derivative of the numerator and the derivative of the denominator. So this is going to be e to the limit as x approaches infinity The derivative of the natural log of x is 1 over x, and the derivative of x is 1. And so the limit of 1 over x as x approaches infinity is how much? It's 0, and e to the 0 equals 1. So we can conclude that the limit as n approaches infinity of n to the 1 over n is also equal to 1. Okay, the next page. We define a sub n recursively by the following. A sub 1 is the square root of 2, that's the first term. And then every other term in the sequence, in general, a sub n plus 1 is equal to the square root of 2 plus the previous term, a sub n, for n greater than or equal to 2. So we want to show some things. We want to show that this sequence is increasing and that it is bounded above. If we can show that, then we can use the monotonic, what do we call that thing again? It's the the monotonic sequence theorem. If a sequence is increasing, that means it's monotonically increasing, and if it's bounded above, the monotonic sequence theorem says that it has a limit. Okay, so the first thing we'll do is show that it's increasing. So we'll observe a sub 1 is equal to the square root of 2, and a sub 2 is equal to the square root of 2 plus a sub 1, which is the square root of 2. So we note that the first two terms show that it's at least increasing that much. A sub 1 is less than a sub 2. What we're going to do is use the induction argument. So this is referred to as the base case. In general, we want to show that the sequence is increasing. So we started with the first two terms, and we observe that the first term is less than the second one. We're all in agreement about that. Square root of 2 is less than the square root of 2 plus the square root of 2. Okay, so what we do is we suppose a sub k is less than a sub k plus 1 for some positive integer k or some natural number k. And the goal is to show that a sub k plus 1 is less than a sub k plus 2. And then we can conclude by induction that the entire sequence is increasing. Okay, we've already established that this occurs when k is 1, right? A sub 1 is less than a sub 2. So if we suppose that a sub k is less than a sub k plus 1 for some other natural number, we want to show that a sub k plus 1 is less than a sub k plus 2. Okay, so if we suppose this, if we add 2 to both sides, 2 plus a sub k, it's still going to be less than 2 plus a sub k plus 1. All I did was add 2 to both sides, so the inequality still holds, right? And then if I take the square root of both sides, we still preserve the inequality. The square root of 2 plus a sub k is less than the square root of 2 plus a sub k plus 1. But this is the square root of 2 plus a sub k is a sub k plus 1 by the recursive definition. So a sub k plus 1 is less than a sub k plus 2. So we can conclude by the inductive argument, conclude that this sequence a sub n is increasing. Have you encountered this induction process before? It's a little bit subtle, but I'll just explain. Sometimes it takes a while for this to click. So in this case, we wanted to show that the sequence is increasing, so we start at the beginning and show that at least for the first 2 terms, it's increasing. And then we assume that it's increasing for another pair of terms, consecutive terms. And we showed that if it holds for a sub k less than a sub k plus 1, it's also going to hold for the next pair, a sub k plus 1 is less than a sub k plus 2. Okay, so what this is telling us then, since we showed that it's true for the base case, a sub 1 is less than a sub 2, this argument right here shows that a sub 2 is less than a sub 3. And this then shows that a sub 3 is less than a sub 4, and a sub 4 is less than a sub 5, and so on. So like I said, it's a subtle type of thing. But for now, we'll just keep going. The next thing we want to do is show that the sequence is bounded above. So the first term, a sub 1, is equal to the square root of 2. So let's note that a sub 1 is less than 2. So that is we're going to use induction again to show that this sequence is bounded above and that 2 is an upper bound. So this is our base case. So assume a sub k is less than 2 for some natural number k. And the goal is to show that if a sub k is less than 2, then a sub k plus 1 is also less than 2. Then we'll be able to conclude inductively that every term in the sequence is less than 2. Okay, so what we do is for this particular argument, we'll add 2 to both sides. So 2 plus a sub k is less than 2 plus 2. And then if we take the square root of both sides, 2 plus 2 is 4. So the square root of 2 plus a sub k is less than the square root of 4, which is 2. But by definition, the square root of 2 plus a sub k is a sub k plus 1, which is less than 2. So I'll take another stab at explaining the induction. We showed that a sub 1 is less than 2. The very first term is less than 2. Then if we suppose that a sub k is less than 2 for some natural number k, we successfully showed that the next term is also less than 2. A sub k plus 1 is also less than 2. So the thing that's going on here, since we showed that a sub 1 is less than 2, and that a sub k less than 2 implies a sub k plus 1 is less than 2, that must mean that a sub 2 is less than 2, which means a sub 3 is less than 2, and so on. So the every term in the sequence is less than 2. So conclude a sub n is less than 2 for all n. Every term in the sequence is less than 2. Okay, now let's find the limit. By the monotonic sequence theorem, the limit as n approaches infinity of this sequence is equal to a finite number. Let's call it capital L. Okay, so I'll write it this way. L is equal to the limit as n approaches infinity of the a sub n terms. But this is also equal to the limit as n approaches infinity of a sub n plus 1. That has to be true if the limit of a sub n as n approaches infinity is equal to L. Then if I just take the limit of a sub n plus 1 as n approaches infinity, I still get to the same limit, right? But a sub n plus 1 that is equal to the square root of 2 plus a sub n by the recursive definition. And so the limit of the square root of 2 plus a sub n as n approaches infinity, using one of our properties from calculus 1, we can write this as the square root of 2 plus the limit as n approaches infinity of a sub n. But this limit is equal to L. So I'll just write what this is. This is equal to the square root of 2 plus L, right? Okay, so the limit L is equal to the square root of 2 plus L. Now all we have to do is solve this equation for L, and that will be the value of the limit. One way to do it is just to look at it and say, let's see, what would L have to be if L is equal to the square root of 2 plus L? Two works. 2 works. But we can square both sides to get rid of the square root. So L squared is equal to the square root of 2 plus L, which is 2 plus L. And we just have a quadratic equation in the variable L. And we can solve this by factoring. So one factor is L minus 2. The other factor is L plus 1. This equation has 2 solutions, L equals 2 and L equals negative 1. But we already know that all of the numbers in the sequence are positive. So we take the positive solution 2. So the limit of that sequence is 2. Okay, let's go ahead and start section 2 from chapter 11. Okay, from chapter 11, section 2, this is the section on series. Okay, we begin with a sequence, an infinite sequence like the ones that we saw in section 1. So let a sub n as n equals 1 to infinity be an infinite sequence. The infinite series, or just the series of the infinite sequence a sub n, is the sum of the terms in that sequence, a sub 1 plus a sub 2, and so on. So we're just adding the terms of an infinite sequence, and we refer to that sum as an infinite series, or just a series. Okay, so the infinite series, a sub 1 plus a sub 2 plus, and so on, can be denoted using the sigma notation. So this just means we're adding the a sub n terms as n ranges from 1 to infinity. Some infinite series converge to a finite number, whereas other infinite series diverge. So we'll look at some examples here. This series, the series of the terms n to the second, where n ranges from 1 to infinity, we're just adding 1 plus 4 plus 9 plus 16 plus 25 and so on. So it's pretty evident that if you keep going, you're going to head off towards infinity. So this series diverges to infinity. This series, we're just alternating 1 minus 1 plus 1 minus 1 plus 1. It doesn't go to infinity, but it doesn't converge to a finite number either. So this one diverges. It doesn't get close to a single number. Okay, the next series, the terms 1 over 3 to the n as n ranges from 1 to infinity. So the first few terms are 1/3 plus 1/9 plus 1/27, and so on. This converges to 1/2. So we can write it this way. The infinite series of 1 over 3 to the n as n ranges from 1 to infinity equals 1/2. Okay, we will learn some things about how to show whether an infinite series is convergent or divergent. And sometimes we will be able to find what a convergent series converges to by looking at the corresponding sequence of partial sums. There will be some series that will just be satisfied to know that they converge, but finding what they converge to is often extremely difficult. Okay, but this next definition is sort of important. Sequence of partial sums. If we're given a series of a sub n terms where we're just adding a sub 1 plus a sub 2 plus a sub 3 and so on, we denote by S sub n the nth partial sum. So in other words, S sub n is just the sum of the first n terms in the series. So this S sub n forms a sequence of numbers. That's the thing to grasp here. So S sub n forms its own sequence, and it's referred to as the sequence of partial sums. So let's see, I suppose it might help if I write a few of those partial sums. S sub 1 is just the first term. S sub 2 is the sum of the first two terms, a sub 1 plus a sub 2. S sub 3 is the sum of the first three terms, a sub 1 plus a sub 2 plus a sub 3, and so on. And you can use sigma notation. S sub n is the sum of the a sub n terms as, I should have put a sub I. Yeah, so S sub n is a sub I as I ranges from 1 to n. Okay. So make sure you catch that S sub n is a sequence itself. So we can apply to sequences some of the things that we discussed from section 1. Okay, so if that sequence of partial sums, S sub n, is convergent, and if the limit of the S sub n is equal to S, a finite real number, then the series a sub n is convergent and its sum is S. Okay, so that is if we add all of the terms from the sequence a sub n and it's equal to S, we can write it using sigma notation. Okay, on the other hand, if the sequence of partial sums is divergent, then the series of a sub n terms is also divergent. So this is what we're saying. If S sub n is the sequence of partial sums, then the limit of that sequence is also equal to the sum of the series. Okay, we'll look at some particular types of series. In this first one, a sequence, a sub n, as n ranges from 1 to infinity, is called a geometric sequence if a sub n is equal to a times r to the n minus 1, where a is not equal to 0. Okay, so each term in a geometric sequence is the product of the previous term and the common ratio. And the common ratio can be found if you divide a sub n plus 1 by a sub n. So just using the definition, a times r to the n divided by a times r to the n minus 1, that simplifies to r. That's the common ratio. The corresponding geometric series, where we just add the terms from the geometric sequence, looks like this. The terms have the form a times r to the n minus 1 as n ranges from 1 to infinity. The sequence of partial sums, S sub n, that's just the sum of the first n terms. So S sub n is a plus a times r plus a times r to the second, and so on. The last term is a times r to the n minus 1. When the common ratio r is 1, the geometric sequence diverges. Because the terms are a, 2a, and so on, n times a. So if you take the limit as n approaches infinity, you just end up at either positive infinity or negative infinity, depending on whether a is positive or negative. Okay, let's find a formula for S sub n. So this is a partial sum. We're just adding the first n terms of the geometric sequence. Okay, first I'll write S sub n out as a plus a times r plus a times r to the second, and so on. At the other end, we have a times r to the n minus 2. The last term is a times r to the n minus 1. So from the geometric sequence, this is the sum of the first n terms. So does anyone know what's coming next? Have you seen this before? Okay, what we're going to do is we're going to multiply both sides of this equation by the common ratio r. So r times s sub n on the left, and then on the right-hand side, multiply each of those terms by r, and we get a times r plus a times r to the second, and so on. At the other end, we get a times r to the n minus 1 plus a times r to the n. Then we're going to subtract the second equation from the first equation. So on the left-hand side, we'll have s sub n minus r times s sub n. And what happens on the right-hand side when we subtract the terms below from the terms above? We get a bunch of zeros. So we get a, but a sub r minus a sub r is 0. Did I say a sub r? A times r minus a times r is 0. A times r squared minus a times r squared is 0. And so on and so on and so on. I didn't write the a times r to the n minus 2, but that's going to subtract with the term that comes before this one. This term minus the same term is 0. And we're left with minus a times r to the n. Okay, then on the left-hand side, factor s sub n out, so we get s sub n times 1 minus r. On the right-hand side, we'll factor out a, so we get a times 1 minus r sub n, r to the n, I mean. And we're trying to find a formula for s sub n, and we found it if we divide both sides by 1 minus r. So we get a times 1 minus r to the n divided by 1 minus r. Okay, we can use this to determine when a geometric series converges. So remember what s sub n is. S sub n is the sum of the first n terms of the geometric series. I'm just going to refer to those as a sub 1 plus a sub 2 and so on up through a sub n. Okay, so the series, the geometric series, will converge when s sub n converges. So we'll note that the limit as n approaches infinity of the sequence of partial sums will exist as a finite number if r to the n goes to 0. So the limit of this is a finite number if the limit as n approaches infinity of r to the n is 0. And we know that what the values of r must be for that to happen. The r values have to be strictly between negative 1 and 1. So the limit as n approaches infinity of r to the n equals 0 when this common ratio r is between negative 1 and positive 1. So do you believe it? For example, if you pick r to be 1/2 to the n and let n go to infinity, well, let's see, 1/2 and then 1/4 and then 1/8 and then 1/16. It's going to 0. If you let r be 1, then the limit does not equal 0 because 1 to the n is always 1. So anyway, when the common ratio is between negative 1 and 1, the geometric series converges. Okay, and you can tell what the sum is going to be when r to the n goes to 0. It's just going to be a divided by 1 minus r. Okay, that's what is stated on this next page. The geometric series, the terms are a times r to the n minus 1 as n ranges from 1 to infinity, which is equal to a plus a times r plus a times r to the second, and so on. It's convergent when the common ratio r is strictly between negative 1 and 1, and its sum is a divided by 1 minus r. And as we already stated, if r is less than or equal to negative 1, or if r is greater than or equal to 1, the geometric series is divergent. Okay, the next two examples are of geometric series. So determine whether the geometric series below converge or diverge. Remember how to find the common ratio of a geometric series? So in general, if you divide the n plus first term by the nth term, that's the common ratio. So we can just use the first two terms. So in this case, negative 4 divided by 3. Well, that's less than negative 1. So what do we conclude about that geometric series? It diverges. So we're done with that one. Okay, the next geometric sequence, 4 plus 3 plus 9/4. What's the common ratio of this one? Three-fourths. So we can find it using the first two terms, divide the second by the first. We get the same number if we divide the third by the second, and so on. So this one's going to converge. And what's it going to converge to? Okay, well, if we factor 4 out of every term, we get 4 times 1 plus 3/4 plus 9/16 plus 27/64, and so on. So we can rewrite this as 4 times 1 plus 3/4 to the first plus 3/4 to the second, and so on, plus 3/4 to the third. Okay, so as an infinite sum, a series, that is, if we range from n equals 1 to infinity, we can write this as 4 times 3/4 to the n minus 1. And you can verify that this is the right formula. But if you remember, so this is the formula for the sum. If the terms are a times r to the n minus 1, the sum is a divided by 1 minus r. So for this one, our a divided by 1 minus r, our a value is 4. Our common ratio is 3/4. So the sum is 4 divided by 1 minus 3/4, or 4 divided by 1/4, or 16. Okay, we're out of time. We'll finish the section 2 on Monday. And on Tuesday and Wednesday of next week, we'll review for test 3. That is all for today.